Hello and welcome back to Data Science Castnet. In the previous video, we introduced some concepts around diffusion for language modeling, and we attempted to train a very small masked diffusion model based on ModernBERT, where you are starting with a bunch of masked tokens and you're gradually turning those into predictions for what the actual real token should be. And we were able to use this to generate some sort of at least vaguely plausible text. So that's kind of exciting, but also there was a lot of issues that we called out there, or things that felt unsatisfying about that masked approach. And so a few of them I call out in a sort of thread after the video. One is, how do you deal with variable length responses, right? Not knowing in advance how many tokens your answer should be. And so in a future video, we definitely should look at edit flows and the ideas there around using substitution or addition or deletion, as opposed to just starting with a bunch of masked tokens of a fixed size. And also like there's some others around blockwise decoding. But then another part of it was this idea of being able to refine your predictions and to correct for earlier mistakes, right? So we talked about how in image models, your early predictions are bad, and then every pixel is evolving over time. And in the video, I called out Paella as one example of a sort of discrete diffusion-like thing for images, but it was based on discrete tokens. And instead of using mask tokens, they would use random tokens from the vocabulary, right? And it turns out that this is nicer in some ways because you get this property of self-correction. A predicted token earlier in the process, you might later have a prediction for a different token that should go there instead. And so that's a very appealing thing that we'll start to look at more today. And then finally, there was discussion around, can we tie this more into something a little bit more continuous, right? So there's this paper from a friend of mine at Sakana AI, large language models to diffusion fine-tuning, where they're working in the continuous space of effectively the logits, right? The likelihoods assigned to different tokens continuous before they get turned into that discrete representation, and doing multiple diffusion steps in that quote-unquote logit space. And so I was saying, what could we apply this to a whole sequence? What would that look like? And so very, very sort of fortuitously at about the same time, or maybe a few days before the previous video, this paper came out, which I finally had a chance to read, called the Diffusion Duality. And so it's a bit of an intimidating paper from a sort of maths and wording perspective. And in this video, we're going to go through it a little bit. I'm not going to dwell on all of the individual equations, but instead we're going to try and distill out the essence of the idea and why it's appealing and why the people who are good at reading all of that maths are so excited about this paper. We're not going to do any practical like model training in this video, but it's going to give us some ideas and some pieces that we can incorporate into future videos. Okay, so that's the sort of vague intro. Let's dive into the paper. And so I'll switch over to Zotero. Okay, so this is the Diffusion Duality published 12th June, and they're going to talk about uniform state discrete diffusion models, which we'll define. Very promising due to their ability to self-correct. And so these are those ones that I was talking about, where instead of just predicting from a mask to a token and then that's fixed, or you try and remask it, these instead, any token could be a random token from the vocab or some other incorrect token, and we're going to try and model the probability of turning that into the correct token and use that to like start with effectively random tokens and progressively refine them. And in fact, we should switch back over to the website for this that has a nice little animation of the final thing they're going to produce. So you see the blue here highlighting the tokens that change. It starts with complete nonsense and it gradually sort of refines and refines, as opposed to masked diffusion like we looked at, which starts with all masks and then gradually unmasks, or autoregressive, which does one word at a time. Okay, so back to Zotero. So yeah, they say these models are exciting due to fast generation and self-correction, but they're typically outperformed by autoregressive models and masked diffusion models. And so in this work, they narrow the gap by leveraging a key insight. These uniform state diffusion processes naturally emerge from an underlying Gaussian diffusion, right? So there's this continuous process underlying these discrete transitions, and they are going to come up with ways to transfer techniques from the continuous Gaussian diffusion world into this application of uniform state diffusion processes, and be able to kind of like translate between these two worlds effectively and take a bunch of tricks that have been figured out for continuous diffusion to apply them here. And so they have some core ideas, like some really core pieces of insight that they show and that they spend a bit of time proving. They also have some additional tricks. So there's some extra strategies that they apply based on insights from this maths that they've done, and then some additional methods like their discrete consistency distillation. And all of these pieces together give you a model that does few step generation that's pretty good, and that's able to surpass autoregressive models in 3 out of 7 benchmarks. So this is still quite a small scale and quite limited, but very promising work to bridge the gap between these different worlds. And so I think let's start with this figure 1 and try and build some intuition here. And so if you are familiar with how like a language model works, for example, you have some discrete representation of your input, right? The input is split up into tokens, each of which is from a fixed vocabulary. Then those tokens get turned into embeddings and fed through the layers of the model. And then at the output of the model, you take the final output embeddings and you run them through the language modeling head, which takes it from that embedding dimension into a single value for every possible token that it could be. And the way we train this is we want to assign a high value to the likely actual token. That's the correct sort of next token or whatever you're predicting, and low values to everything else. And if we take those so-called logits, right, those predictions corresponding to how likely the different tokens are, and we apply the softmax operator so that they all sum to 1, then we get kind of predicted probabilities. How likely is it that any given token is the actual next token? And if we want to sample from that, we could say, what is the most likely next token? We'd use the argmax operator, right? Saying which of these possibilities we have, if you have a vocabulary size k, we have k different possibilities. Each of them is assigned a number by the model. If you're doing language modeling, we pick the one with the highest probability, and that's our predicted next token. And so you can see there already we have this underlying continuous distribution, right? The different logits, or the different probabilities, depending on how you like to frame that. And we're transforming that into a discrete choice of saying this is the one we actually choose using this argmax. And so they have here the ZT is the sequence you're looking at, right? Where you'd have starting at the data and then moving more and more corrupted, right? More and more changed. And if you're looking at it in this discrete world, there's just a certain probability at any given time whether that token is going to be kept as is or whether it's going to be changed to a random one out of k possible options. But underlying that, you can also imagine that there's this more continuous smooth distribution of one distribution where the logit for the correct token is high and everything else is low, moving into this much more chaotic one where you have a Gaussian distribution of those sort of underlying latents, these Gaussian latents that they talk about. So this ZT is going to be the discrete version, this WT is going to be the underlying sort of hidden continuous one, and the paper is going to be trying to find ways of applying insights from one of those sides to the other. And this is really exciting because once you can do that, this Gaussian diffusion has been well studied, right? Introduced and developed for images, famous models like Stable Diffusion, for audio, for video, and there's lots of techniques that improve upon the kind of initial implementation, right? So you have consistency models, you have simple diffusion, you have things like Karras et al. Showing ways of thinking about the noise schedules and the sampling, and then you have distillation schemes that give you faster generation. I think this is consistency models and different ways of distilling down. Okay, so that's the framing. Their objective is to figure out a way that lets you take these training and inference techniques and apply them to diffusion models, discrete diffusion models for language, and to figure out how to do them with few steps. They come up with their framework Duo, enriches the design space by incorporating Gaussian diffusion, surpass models on a few different benchmarks, although it's still small. Okay, so I think that's the core idea of this paper and the core aspect of it. Maybe before we look at the maths, I'm going to give my best attempt at highlighting what this might look like in a more hand-wavy way. So let me switch back over to a nice little scratch pad here, and we'll dive in. Okay, so we can imagine we have our input training data, the cat, sat on the mat. You're going to have to denoise my handwriting. Okay, and then we can pick some time step, right? So we're going to have a t between 0 and 1, and this is going to go from almost no degradation to almost complete degradation. And so this is going to tell us in this discrete case whether or not we will replace one of these tokens with a random token from the vocabulary, right? So if we imagine a value that set us replacing with a 40% chance or something like that, we could have something like cat becoming the rug sat on IP address 1 mat, right? Like 2 random tokens from the vocabulary, completely unlikely. And so we're going to take this new sequence here, the sat on mat. We're going to feed this through our model, like so. And the model's job is going to be to predict for these tokens, just like with normal language modeling perhaps. We want to predict a high value for the correct actual token, right? And a low value for the incorrect ones. And so on. Okay, so we want to make a prediction of the distribution of these tokens that should reflect like what the actual token is, and to learn from what the input data is. We can refine this by also telling the model the time step, right? So feeding it in the fact that this was t is equal to 0.4 or something like that, but that's not necessarily strictly necessary. And so then when we want to sample from this, we can start at the equivalent of t is equal to 1, right? The most corrupted case, and we just have 5 completely random tokens, and then we could see what the predicted distributions are, choose a few of those to turn into the predicted tokens. But key to this approach versus the masked case, right? When we have the mask diffusion, once you've gone from mask to some text, there's no way to correct that without just randomly applying extra mask tokens and then unmasking them again and hoping that you get a better prediction. Whereas in this case, if I start with, I'm not going to actually write things here, but blank, 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 but this is, fish, hat, mug, whatever. This one is this one is dog, and then sat on the cat mat or something like that, right? If I'm feeding this through and a few of these are still random, my predictions for this one later, once the rest of the sentences kind of somewhat emerged, it might be more obvious that, oh, this actually has a chance of being cat. And so if I want to sample, even though I've already made a prediction for this, there's no reason I can't do that again, right? There's this chance to self-correct. That's the big key thing here. Okay, and so in our Duo world, we're going to be pretty much doing this. Our training is going to start with a clean sequence of tokens. So we'll have our clean sequence of input tokens. We'll draw a time t. We will have some value alpha that determines whether or not the tokens are kept or replaced. And early time steps will barely change the sentence. Later time steps will change it quite a lot. And then we'll have a model that sees this noisy sequence and tries to predict the distribution of the original clean tokens at every position. And the loss function is going to be some comparison, right? Like maybe the KL divergence type thing between the true, probability of what each token should be and then the model's guess. So we're going to compare those two. We're going to average over the different time steps. We're going to be sampling different time steps every time. And that average over time steps is going to be something like the negative evidence lower bound, I think they call it in the paper. Don't quote me on that being that. They have their special formulation, which is kind of effectively just a weighted cross entropy, right? So that's the thing with this paper is we have all of this theory, and it's going to come out to looking very much like, regular masked or whatever regular language model training, where we have some sequence and then we have some targets, and for those targets we're trying to predict the the logits that match the true value with some weighting, but it's all going to be justified and built around ideas based on understanding that these discrete noisy sequences are actually related to a continuous noisy latent representation with its own equivalent of the different time step alpha, whatever you want to call it, corruption that's happening. And by thinking about this continuous case, we're going to justify the approaches and the loss functions and the calculations, and we're going to use that to inform various improvements to the training. And so I think that's going to inform ways that they cut down on the variance and tricks that they do early in training, where instead of feeding in a sequence based on the argmax operator and this like pure discrete version, they're going to use a sort of softmaxy scaling that's through a little bit more. So anyway, so there's lots of nuances, but this core idea of take a sequence, corrupt it a little bit, try and predict the clean tokens, and rinse and repeat until you've got a model, and then to sample, you're going to start with completely random noisy tokens and gradually refine them. That's the core idea, and everything else is going to be around how do we justify this, and then how do we make it faster with fewer steps based on the hints from this underlying continuous case. Okay, so that's a lot. Let's see if we can pull out some pieces of that from the math without getting too deep into notation or worrying too much about the hard bits. State transitions based on this alpha value and how much it's changing, right? The likelihood that any given token turns into any other token. Gaussian diffusions in this sort of noisy space. Consistency distillation being, like we said, less noisy sample with the teacher, and then the student trying to match that on a more noisy sample. Okay, and then linking that into how do we bridge between the two, and the key insight being this argmax operation transforms the Gaussian diffusion into a uniform state diffusion, and this equation here is going to relate how this diffusion transform operator ties into the sort of continuous Gaussian diffusion, I don't know what you'd call it, distribution function or process. I'm going to call lots of things processes that probably technically aren't processes and maybe annoy people who actually understand a lot more of the maths. Okay, but there's this fundamental connection that these equations give us between the discrete case and this underlying continuous case. Okay, so here's a nuance that we might as well look at. Greedy tail sampler. So we're feeding in noisy sequences, and we're predicting for every position in the sequence what the clean version of that token might be during the final denoising step, instead of sampling the clean sequence by looking at just taking the predictions of the models and sampling that based on some temperature, or so instead of drawing from this distribution, right, because the model is going to predict a distribution for what the output could be, instead of drawing from that distribution, we are instead going to take the most likely token as predicted by the model. Very, very sensible. When we were doing our sampling from our masked one, we were always doing this. For any given token that we decided to unmask, we would take the most likely token the model predicted, whereas here, for every step apart from the final one, we're going to draw from that distribution, and you can imagine later messing with the temperature value of how we're scaling those predicted quote-unquote logits before we take the sample. Okay, and so that gives us nice sampling. Other parts of this, curriculum learning. So starting with easier to denoise noise patterns and moving to more challenging ones. One way that you could do that would be to tweak the mask ratio that you use, right? And so start at like maybe only doing lower mask ratios. But they also here talk about how the argmax operator is related to tempered softmax. So instead of having the argmax, like just a 1 where the value is highest and 0 is everywhere else, have a softmax with this scaling temperature and pushing that very, very low. And so you get an almost 1 and then lots of almost zeros, but at least some other signal there. And so the theory behind that is to make it easier to recover the clean signal from the noisy version. And so this is like a way of like turning down the difficulty earlier in training. Totally sort of orthogonal to the main thrust of the paper in some ways, but I think because of this inspiration and this trick, it lets them learn more early in training and gives them better losses earlier. Okay, so that's one trick. Their loss function, I think, comes quite a bit later. That trick that they do of the softmax with this temperature versus argmax gives you lower variance during training. What else? Oh, and then discrete consistency distillation is the other big part of this paper. And so that's going to be this approach where they take a noisy sequence. Well, they take a sequence and they make 2 different versions of it. And they do this by, you can imagine like applying noise in the continuous space and then discretizing that with the argmax. And then by using the same noise but 2 different values, right? 2 different, so you have the same noise epsilon but 2 different t's for the time step of the teacher versus the time step of the student, and then getting the argmax. So you'll end up with 2 sequences, one of which is more corrupted than the other, but they're both like sort of on the same trajectory, as it were. And then you can say like, now I'd like the student to predict the clean sequence the same way the teacher predicts it, but it has a slightly harder task because it's seeing a noisier version of the latents compared to the teacher. And we're going to just minimize the KL divergence between the predictions from the teacher and the predictions from the student. And they do a number of rounds of this and update the teacher after each round. And so the insight for this is just that you have a model that's learned to predict the clean version of any noisy input, but in such a way that you hope that you recover a good clean sample after many prediction steps. And now we want to do it with very few steps, and so we take the model that's good at predicting over many steps and we give it an easy prediction with less noise, and then we take the model that we're actually training based on that model, give it a harder prediction, have it try and match the prediction of the teacher model, which is given the easier task, and repeat until it learns to do harder and harder predictions, let you take bigger and bigger steps. Okay, so they do this on a number of tasks. They see pretty decent performance. They compare it with autoregressive setups and other different diffusion approaches. They find this works quite well. Their greedy tail trick of using the greedy argmax sampling in the final step rather than drawing from the predicted distribution gives them a slight boost. I think that's a lot of the paper. But like I said, the very exciting part of this is that this gets around some of the mask diffusion model pieces that just feel suboptimal. They say we've realized and thought about how these discrete tokens that we're looking at are kind of tied intimately to this idea of some continuous version happening under the hood. And the models are all predicting logits first and then sampling from that predicted distribution to get your discrete tokens. And so by cleverly thinking about how those 2 worlds are linked, we're able to incorporate some designs from continuous diffusion world into our discrete world. We should look at, I guess, equation 47 of their actual loss function if it's even findable. I don't think I'm a little chicken to try and explain this, so maybe we won't. But they end up with their F duo, their loss function, which you can think of, I think, as basically the sort of loss that you'd imagine intuitively, but with different weighting. And so here is a nice picture of their generative process. You start with a sequence of tokens that make sense, and then at any given time there's some chance that they transition into a random other token from the vocabulary, and you're trying to learn to predict the clean tokens from these noisy tokens. And so at t equals 1, you just have completely random samples. And at every stage, you're predicting some that transition. Some of them you get correct and they stay that way. Some of them you might pick the correct one and then pick the wrong and then pick the correct one again. Some you might pick a different prediction. So this is where, like, if we were doing gradual unmasking and we unmasked these 3 at the first step, they'd all actually be wrong. But here it allows us to refine this one and say, oh, actually that might be data. And then refine this one and say, oh, that's also 4, and this one we predict is going to be dual. And so you have this like progressive refinement, progressive decryptification that is what diffusion is in its essence. That's makes it so powerful. Okay, so I think that's about all on this paper. If we go back now to thinking just about how this relates to our previous work, when we had our modern BERT model training, and then even when we were doing our fine-tuning, we had this thing where we'd say, these are the ones that we're going to tweak, right? And for 80% of them, we will replace them with the mask token. Otherwise, we'll replace them with the random token from the vocabulary. This, we were actually doing the kind of training that this duo approach, this uniform state, what do they call it? Uniform state discrete diffusion training might entail, where you're replacing tokens with random ones from the vocab. And so we can imagine for some experiments cranking this up and saying, rather than using any mask tokens, why don't we mask more and more of our input sequence with random tokens and learn to undo that, and then study very carefully the maths, or if there's code released, how do we formulate our loss based on this type of training? Is it just the cross entropy, or is there some weighting you have to do based on the chosen time step and so on? And so I think that'll be interesting to explore. And then, yeah, ideally we can maybe try loading their models. I think they do have models up on Hugging Face and at Google Colab. So that could be potentially a future video if I get into this and if I manage to train modern BERT to be a model like this, and we can compare it with our master approach. The downside is we have this modern BERT model that was trained on unmasking masked tokens for, I think several trillion tokens of training. And so it's very well suited to us then adapt that for our masked diffusion, whereas it was only like 10% of 20% of the tokens, so a very small fraction of the total tokens that were replaced with random tokens. But hopefully we'll be able to reuse the useful representations that it learned from the mask task. Yeah, so maybe that's a future video. If I don't get to it, it's a good project for somebody else. In the next one, we'll look at the other flaws that I talked about, specifically the having to know the length in advance, and other aspects around that. So we'll take a look at edit flows. But yeah, that's it for this one. I really hope you've enjoyed exploring text diffusion with me. I hope this is useful. I'm kind of sharing as I go, so apologies if I've made any mistakes. I'll put corrections in the comments. Like last time, I'll put a thread up on Twitter if anyone wants to start the discussion. And I look forward to seeing you in the future video. Thanks for watching.